When we talk about nuclear fission, it is a highly controversial subject because people are very polarized with regard to nuclear power. Um, Probably the most polarizing aspect of nuclear fission is its use as a weapon. And in fact, if we go back in time, look at the history of nuclear weapons, very shortly after nuclear fission was discovered, it was weaponized. It was really just before World War II where we even saw that a fission reaction, a chain reaction, was sustainable. And by the end of the war, we had built a bomb. Now we're going to talk about the development of two different fission weapons. Today's nuclear weapons are, in fact, much more horrifying and much more powerful. But these were the Fat Man and the Little Boy bombs, which were dropped on two Japanese cities. And again, this is a very controversial subject, and I apologize, but we'll try to keep it as a more or less a discussion about the technology itself, without talking too much about whether it was justified in using the weapons, because again, there's a very polarizing topic. So the Manhattan Project was developed during World War II. And again, when nuclear fission was discovered, the potential for the energy that could be released in a fission reaction was realized almost immediately. And so Szilard, of course, came up with the idea of a fission chain reaction and urged Albert Einstein to write a letter to FDR, who was president at the time, to develop a nuclear weapon for fear that Nazi Germany was in the process of also trying to develop a weapon. Really, the way it's told is that the United States and its allies worked on the Manhattan Project to try to outrace the Nazis in the development of this weapon. So the Manhattan Project, it was just a code name. It really didn't have much to do with Manhattan at all. All of these secret defense projects are given different code names. Manhattan was chosen for this one. General Groves was the person put in charge of this. He had been involved in the construction of the Pentagon and was a very adept at handling logistical problems. He appointed a head scientist by the name of J. Robert Oppenheimer, and Oppenheimer essentially conducted the research and development that led up to the two devices. And most of the experimental work, most of the research and development was done in Los Alamos, but quite a bit of work was done throughout the country. Now, this project was very, very costly, and it created quite a bit of upheaval in terms of people's lives. But again, this was during World War II, so the country was going through a tremendous amount of stress related to the war effort itself. Now, if we look at the Manhattan Project, again, it was happening all over the country. The first fission reactor was actually built in Chicago, as we discussed in part one. And of course, this was built in a squash court at the University of Chicago. But it was soon realized that this effort had to be relocated. And Oppenheimer had spent his summers in the mountains of New Mexico, in Los Alamos, and really made the headquarters for the development of these fission devices in Los Alamos. And they built an entire lab around this project. When I was an undergraduate, I had the fortune of actually working out at the Los Alamos National Laboratory. Of course, it was very different in the 1980s than it was in the 1940s. I'm dating myself, I guess. 1930s, 1940s. But again, here's where the bomb was actually put together. There were two fronts that they worked on. One was the production of uranium, which was done in Oak Ridge. This was done at the Oak Ridge National Lab, or what is today the Oak Ridge National Lab. And the idea was to separate uranium-235 from the other isotope, uranium-238, to produce weapons-grade uranium. The other direction that they were headed with this project was to actually create plutonium. And plutonium is an entirely synthetic element, meaning it doesn't really exist in any high quantities in nature. And this was done through a breeder reactor in Hanford, Washington, or the Hanford, what is now the Hanford labs in Washington, in Richland, Washington. So the uranium and plutonium was developed at two different sites. The first test of a device was done on a plutonium device. It was called the Gadget. This was done in Alamogordo, New Mexico, not too far from Los Alamos. But again, the first two weapons, and the only two weapons that have ever been used in war, were a uranium device and a plutonium device. Both of these were fission bombs. And again, you can see all the different locations where other work was done for this project. So this was a massive, massive undertaking, during the time that the United States was in this war effort. And the fear, of course, was that Nazi Germany was going to beat us to the development. Of course, Germany was defeated before this weapon was developed, and they never really got close by all accounts that we have. So the focus then was to end the war in Japan. And of course, the dropping of the bomb on Hiroshima and Nagasaki, in all effects, ended the war. Okay, so again, we talked about a two-pronged effort at Oak Ridge. They were setting out to separate uranium-235 from uranium-238. You can't make a nuclear weapon. You can't make a fission bomb from uranium, which is mostly uranium-238. In fact, you need to get to at least 90% uranium-235 in order to produce such a device. And it's not an easy thing. When we separate uranium from the ore, it can be done by chemical processes. I mean, for a very long time, human beings have been very good at smelting ore into different metals. So, creating uranium in a pure metal was really not a big deal. However, because chemically, uranium-235 is identical to uranium-238, there's no means of chemical separation. So they had to come up with something different. Now, the first idea they came up with, which was made by Dr. Lawrence, which Lawrence Livermore Laboratory is named after, was magnetic separation. The idea was to accelerate the ions of uranium and then use the fact that uranium-238 is heavier. It's going to have a larger radius when placed in a magnetic field. This magnetic separation was attempted first, but then it was found that gaseous diffusion, where the lighter isotope will diffuse through a barrier more easily than the heavier isotope, was a better way to go about this. In fact, we never received enough uranium from the magnetic separation process to even create one bomb. It was really diffusion. At the Hanford site, plutonium-239 was synthesized from uranium-238. This was done in a breeder reactor, and this led to the development of the Fat Man device. And this had its own challenges. Plutonium is something that very, very quickly undergoes fission. So we couldn't create a fission device the same way that we could for uranium. And the uranium what they would do is they would have a subcritical mass and then slam another subcritical mass into it and initiate a rapid supercritical fission reaction. With plutonium, if you took two subcritical masses of plutonium and started putting them toward one another, the fission reaction would cause both to actually vaporize each other before an efficient reaction could take place. So implosion was developed for that type of bomb. Now, here's the little boy. This was the second fission device, the second atomic bomb to be detonated, but it was the first atomic bomb to be used against civilians. And this was dropped on Hiroshima. And the idea, again, was you had this uranium subcritical mass at this end, and then another subcritical mass, which would insert itself into this. Now, this had to be done very, very rapidly because as the two masses approached one another, they would go critical. And if this wasn't done fast enough, they would superheat and essentially the bomb would fizzle out as the two masses would vaporize. So the idea here was to actually create almost like an internal gun barrel. They would fire the uranium bullet at the subcritical mass. The two would combine, very, very rapidly before they could begin to generate too much heat. And because this was a supercritical mass, the chain reaction would happen very, very rapidly, and most of the uranium-235 would fuse as a result. I'm sorry, would undergo fission as a result, not fuse. When a fission bomb detonates, we're very, aware of the mushroom cloud, which is oftentimes associated with these types of detonations. What we probably don't realize is that the bombs are not in contact with the ground. What they actually do is they'll detonate them above the ground. This allows the fireball to expand and do the most amount of damage. When the uranium detonates, it superheats the uranium to millions of degrees. So it's essentially, it's almost instantaneously turned into an extremely hot plasma, which is radiating X-rays. And again, the bomb would be detonated about 600 meters above the ground, and this would produce basically two thermal pulses, or two pulses of energy. The first pulse would be X-rays and UV light, and it would create a tremendous amount of thermal damage to anything that was exposed. If you were out in the open, anywhere near ground zero and you're unprotected, it would kill you almost instantly. The amount of X-rays and the amount of UV light that would penetrate into your body would end your life very, very rapidly. The fireball would then expand, and as it expands, the wavelengths would become longer and longer until finally it was primarily radiating infrared. So this is sort of the second stage of the thermal pulse, which if the first wasn't bad enough, the thermal radiation would then get you. Now, the expanding fireball is expanding, it has a tremendous amount of energy. It's expanding at supersonic speed, and therefore it produces a shock wave. So this would be the third source of destruction from this bomb. So very, very devastating device because of, again, the initial ionizing radiation, the secondary, the thermal radiation, and then, lastly, the physical force from the shock wave would, create a tremendous amount of damage. And here we can see the actual progression. At first, we see a house, this is a model which was actually built in the desert when they detonated one of the bombs. You see the surface of the house is at first vaporized. This is due to the initial radiation blast. Again, the X-rays in the UV, followed by the strong infrared, would basically vaporize the surface of these different objects. And initially, and unfortunately, the video is blocking this a little bit. Initially, there would be only this radiative damage, and now you can see the shock wave has arrived. You can actually see the shock right here. And it's beginning to tear this house apart, and very, very quickly, the building is destroyed as a result. So that's really what we see with these devices. Of course, it was not just the intense radiation that would cause thermal burns on people. And I apologize for the photograph, but we can see the actual textures of the clothing that this lady was wearing, and how it burned into her skin. So not only did you have to worry about these thermal burns, but also the radiation that would be left from the uranium undergoing fission would leave behind a tremendous amount of residual fallout, which would, again, if you inhaled it, attack your respiratory system. If it got on your skin, it would put penetrating radiation into your body. If you drank any contaminated water, again, as an internal hazard, the fallout is bad enough. If it gets on you, it's even worse if it gets in you. So again, the first weapon that was actually dropped on a city during wartime was dropped on Hiroshima. And again, this was the uranium fission bomb that was developed, the little boy bomb. And the bomb vaporized most of the center part of the city, killed about 70,000 people, but according to estimates, it was probably more like around 200,000 people that eventually died as a result of their injuries or through cancer. And just a note here, these bombs are much less powerful than today's bombs, at a few tens of kilotons versus the megaton warheads that we have. Now, plutonium is not, as we said, a naturally occurring element. Plutonium has to be manufactured, and it's considered to be a transuranic element. Essentially, it's an element that's heavier than uranium, and it is, if you think about the way that some of these elements were named, uranium was named after Uranus, the planet Uranus. Neptunium was named after Neptune. Of course, plutonium was named after Pluto, the dwarf planet. So again, plutonium is not long-lived enough in order to have survived since its creation in a supernova explosion. So we have to create it in a reactor. And it is basically created when we add a neutron to uranium-238, and that decays into the final plutonium. So this has to be done in what is known as a breeder reactor. So again, the most common isotope of plutonium, plutonium-239, starts with a non-fissile isotope of uranium, the 238. And in reactors, plutonium is being created all the time because we don't use pure U-235 in reactors. So what happens here is that any U-238 is converted into plutonium, and then the plutonium, being fissile, will then be converted into daughter elements from that. If we operate the reactor correctly, the reactor will generate plutonium-239 from the less useful 238, and then that can be used to create energy, because plutonium can be more, have a higher cross-sectional area for thermal neutrons than uranium-235. However, if we take plutonium or we generate plutonium in a breeder reactor, usually a fast neutron reactor, it's a very effective breeder reactor, the plutonium won't burn off, and essentially we can create bomb-grade material. So here's how the reaction basically works. Uranium-238 inside the reactor doesn't normally participate very much in the reactions. If it captures a neutron, it becomes uranium-239. This is not a stable isotope. This will quickly, via beta minus decay into neptunium-239. Neptunium-239 is also not stable, okay? It will also beta decay into plutonium-239, and that is a fissile isotope that can be used to create a bomb. So again, starting with uranium-238, captures a neutron. Usually, this is a neutron that's been thermalized with a moderator. It's turned into, it becomes uranium-239. I had to think a little bit about that, again, with the fast reactors. As it beta decays, becomes neptunium. As it beta decays, becomes plutonium. Now, during the Manhattan Project, the plutonium bomb, again, was being pursued at the same time that they were separating isotopes at Oak Ridge. And this is a picture of what was known as Reactor B. It's actually the building where they had Reactor B. This is actually Reactor B. Nothing, amazingly clever about how they named this thing. I don't know if there was ever a Reactor A. Maybe they call this Reactor B because the Chicago Pile 1 was perhaps the first attempt. Maybe there's another prototype attempt. But you can actually visit this reactor today. You can see they've roped off this area, and they have some display monitors here. But the original reactor is still back here. This is a graphite reactor that had operated with unenriched uranium and converted that into plutonium. This reactor was supplemented and eventually replaced by two other identical reactors, D and F, and those were eventually replaced by other reactors. Now, again, oh, by the way, in this reactor, what they would do is they would put in the uranium pellets, and this was very much designed to convert uranium into plutonium. So you could think about these pellets as sitting in these different chambers. I don't know how well you can really see this, but all of these are tubes, and you put your uranium in there. They would sit in a whole matrix of all these graphite blocks. And after a time, enough plutonium would build up on them, and they would push the plutonium out the other side. It would fall into a pool of water behind this, and then it would be remotely scooped up after it had enough time to decay some of the other fissile elements, daughter products. And then that would be taken to a separate area where it would they would extract the plutonium from the spent fuel pellets. So they're constantly putting in new fuel and taking out the old fuel and extracting the plutonium from this. This reprocessing went on through the operation of this reactor. So once the plutonium was chemically separated, it was put into a pure form. The problem with plutonium is you can't build it up into too large of a slug, otherwise it will go critical, and it can cause a whole bunch of problems if it suddenly goes critical, because you've got a runaway fission reaction. Like uranium, it's about twice the density of lead, and it's moderately radioactive but highly toxic. So this had to be machined in glove box areas where none of the plutonium could expose the workers. This is the Fat Man bomb. And if we look at the Fat Man bomb, we can see how they came up with a name. I'll go back to the Little Boy bomb. Here's the Little Boy bomb, and you can clearly see it's long and thin. The Fat Man bomb was actually the second device created with plutonium. The first device was called the Gadget, and it was demonstrated at Alamogordo, New Mexico. It was the first time we ever detonated a fission bomb. So once they figured out that that works, they put that into a weapon, and that became the Fat Man bomb. Now, again, remember, there were two paths that they were going on in order to separate the fissile material. The first was to get uranium-235 to weapons grade condition. And this was done at that Y25 building where they did the diffusion separation. Okay. Unfortunately, they, even though this was the largest building at the time, they only had enough uranium, I believe, for 2 bombs. So they didn't want to test that bomb. They wanted to just use it and hope that it worked. The plutonium bomb was a little bit more, I guess, had a higher degree of uncertainty whether or not it was going to work. So they did test that bomb first, and that was done at the Trinity site, which you can also visit in New Mexico. So here's how it would work. Again, they couldn't have the gun barrel device like they had for Little Boy. If they tried doing that, the problem was due to the contamination with other plutonium isotopes, as the two got closer to one another, the reaction would have destroyed both samples. Even the gun barrel couldn't assemble them fast enough. So they came up with another way of going critical. What they did is they took a hollow sphere of plutonium. Now remember, criticality depends not only on how much fissile material you have, but how concentrated it is. So the idea was if we could go from the non-critical hollow device, just almost critical, but still non-critical, the non-critical hollow device, and then crush it to become supercritical, you would get a detonation. And the way that they did it is they surrounded this with high explosives, but it wasn't just about packing a lot of explosions around it. These were high explosives, but they were shaped such that some of the explosives detonated faster than other explosives. And what they were able to do is create this spherical blast wave, which imploded inwards. So on the outside, you would have, of course, the explosion going outward, but at the same time it was going inward. This would push this layer of aluminum, which is basically just like an inertial ram. It's just like a ram that's going to crush everything. This would crush the plutonium pit, which was the hollow sphere. And then at the center of that, there was a polonium beryllium initiator. And the initiator, as it was crushed, would release a large number of neutrons. The neutrons would flood the plutonium pit as it was crushing and going critical. And you would get a very rapid fission explosion as a result of the whole sphere being crushed. So it was we call it an implosion device because we use explosives to inwardly crush the material and make it go critical. And this is what a cross-section of this look like. You can actually see the darker brown and the lighter brown, which would represent higher velocity and lower velocity detonations to create a very focused, inward spherical shock wave. And at each detonation point, we would trigger the highest explosives simultaneously. And they would come together to superimpose one massive imploding shockwave. And here's the Trinity test. This is a animated GIF of the explosion. Now, this device was actually detonated in a tower, and you can see it's spherical and it's wired up. Those are the wires to essentially detonate the high explosives. And it's called the Gadget. It was detonated in July 16, 1945. And if we look at the timeline of all this, the Little Boy bomb was dropped on, I thought I had the date here. Unfortunately, I do not have the date. But the Little Boy was detonated soon after this bomb was tested. And the Fat Man bomb was dropped on Nagasaki. It was detonated on August 9th, 1945. And fewer people died because of this bomb, even though it was more powerful. And that's because Nagasaki sits in a valley, and the shape of the topography actually helped protect more people. So the death rate, fortunately, was lower for this. Now, Japan soon surrendered after this, but again, it's highly controversial as to if we should have dropped the bomb. I'm not going to, debate, the ethics here. But back in the time, the war was having a profound effect on everybody's lives. People were losing relatives left and right. So there was a profound push to end the war as quickly as possible. And many proponents of the devices, of the fission devices, argued that more people were dying in the fire bombings in Tokyo, that if we could shock the Japanese and prevent the need to invade mainland Japan, where we thought we'd probably lose about 1 million people just on the invasion. Although it was horrific that people would die due to the nuclear bombs, it was seen as a lesser of two evils. On the flip side, many scientists argued that it should be done as a demonstration, that we should explode it out in the open water where the Japanese could observe its devastating effects. However, others argued that this wouldn't have had the shock that it had. So in any case, it is a very controversial event, the use of the bombs. And, we don't really have a good answer in terms of, was this the right thing to do? Certainly, there are arguments that could be made on both sides. Unfortunately, once something like this is used, it's used over and over again. And we haven't had any nuclear weapons used since this time. So hopefully we as human beings know better now. In any case, plutonium has other uses. The plutonium isotopes that are most common from breeder reactors, because they don't occur naturally, are plutonium-238, plutonium-239, which we just discussed, which is used in weapons, plutonium-242, and plutonium-244. It's plutonium-238 that has uses as a radioisotope in generating electricity for space probes. And this radioisotope thermoelectric generator is very interesting in that plutonium-238, because it has a short half-life, if you have enough of it together, is always hot. I mean, thermally hot, not just radioactively hot, but always generating a lot of heat. And engineers decided, well, we can use the heat generated from this to use basically a thermocouple. Thermocouple is a device where if you put a temperature gradient across it, it'll generate electricity. And essentially, you've got a heat source, you have your electrically generating a thermocouple, and that will produce electricity. So this is a thermoelectric generator. This is an actual plutonium pellet, which has been surrounded with ceramic, and you can see it glows red hot. And that's not because it's been heated, that's because it is self-heating. If you just let that sit there, that would stay hot all day. In fact, with its half-life of 87 years, it will have that intensity of heat for one half-life. It'll be reduced by one half. So here's what the generators look like. They have the heat source in the outside. You have the thermocouple layer between the two, which is actually made of silicon germanium. And then you have the heat radiators that radiate the heat off into space, because again, this works like a heat engine, but with no moving parts. The heat has to flow from your hot reservoir, which of course is the plutonium, to the cold reservoir, which is open space. And as it does so, some of that work can be used to move electrons and generate electricity. Now, plutonium-238 is not fissile, okay? So this can never be used in a bomb. But one of the concerns was, if something happened to a space probe that used one of these generators and it blew up during launch, what would happen to the plutonium? Well, typically these are launched where the thermoelectric generator is going to be protected enough or armored enough that it would survive a launch disaster. And engineers claim that you would be able to recover the generator pretty much intact, even in the worst type of launch pad mishap. But it's been very successful in terms of helping power different space probes. And again, once you get beyond the orbit of Mars, you don't have a lot of solar energy out there. Our solar panels have gotten good enough where we can send spacecraft such as Juno and JUICE out to Jupiter and produce enough electricity. But on the surface of Mars, where we have a lot of dust that covers up the solar panels, generating electricity has become a problem. And as soon as we go beyond Jupiter, okay, we need another source of energy besides solar energy, because at Saturn, which is 10 times further from the sun than we are, it only gets 1% of the sunlight that we get here at Earth. So here, this is actually the New Horizon spacecraft, which was sent to Pluto. So if you've ever seen any pictures of Pluto, this was the spacecraft that went there, and you can see the radioisotope, meaning plutonium, thermoelectric generator, which basically has powered the spacecraft and continues to power the spacecraft as it heads out of our solar system. And here is the Mars rover. This is Curiosity. Looks like Curiosity given the mast cam. And it is powered by a thermoelectric generator back here. Okay. These thermoelectric generators, they were used in the Pioneer missions, which were the first spacecraft to explore the outer solar system. They were used in Voyager 1 and 2, which currently are the most distant spacecraft from Earth. They're used for Viking 1 and 2, which were the first lander missions to Mars. Used in Ulysses, Galileo space probe, which visited Jupiter, Cassini, which visited Saturn, again, New Horizon. And now they're being used on Mars because the Spirit and Opportunity, which were older Mars rovers, used solar panels, and those solar panels got covered with dust. So, of course, they became non-operational as the dust accumulated on their solar panels. Now, by using these radioisotope generators, these rovers can keep going as long as the thermoelectric generators can generate enough heat and enough electricity. And again, oh, okay, here we have the list. Cassini had 3 of these. New Horizon had 1. That's what we saw in that image there. Galileo had 2. Ulysses had 1. And as I said, Voyager 1 and 2, Viking 1 and 2, Pioneer 10 and 11. And Curiosity and Perseverance are both operational right now on the surface of Mars. And even the Apollo missions had a thermoelectric generator to help power some of their scientific equipment. And again, here is a picture. This is I think this is Perseverance. I want to say Perseverance. Although I'm looking at the wheels and it almost looks like Curiosity. But this is the thermoelectric generator. They're very similar as rovers go. But the plutonium is at the center of the cylinder, okay? It's surrounded by your thermocouple, the silicon germanium, and then you have the radiators, which will radiate the energy into space, and that provides you with your cold reservoir. It's essentially a heat engine that operates to generate both heat to keep the spacecraft warm and electricity to keep powering all the instruments and charge the battery. So again, that is part 2 of nuclear fission. Hopefully I was able to focus on the physical principles related to it. Obviously, radioisotope is not fission, but it's a fission product. We use breeder reactors to generate this plutonium that helps power these spacecraft.